continuing on in 10.5, we get to that we have two more tests. We have the comparison test, which says suppose you have two series in which the sequence part of each a sub n and b sub n are both positive. They must be positive. Then, looking at if b sub n is bigger than a sub n for some number, it doesn't have to start in the beginning being bigger. It could after a while get bigger or smaller for that matter. Then, this is the conclusion. Our conclusion is that if the bigger converge, then the smaller will converge automatically. And if the smaller diverge, whatever is bigger than that will diverge guaranteed. Now, those are two useful conclusions. Two useless conclusions will be if the smaller converge, that doesn't tell you anything about what's bigger. That's one case that's useless. And if the bigger diverge, that doesn't tell you much. I'm going to leave that as a note. So, if the series with, not a sub n, if the series of a sub n converge, that doesn't tell you anything. And if the series of b sub n diverge, that doesn't tell you anything. But this is what we know. If the lower diverge, anything above it will diverge. And if the bigger converge, anything beneath it will converge as well. So, directions: test the series for convergence or divergence, use the comparison test. You notice in these problems we only have one series. We have to come up with the second series, and this is how we do it. We get rid of certain values. We get rid of numbers first because we have a p series. Plus 1 is standing in the way. Of course, I could use the integral test on this, but they specify to use the comparison test. So what I do, I take the term that's varying with the constant, and I get rid of the constant. Now, if I was to ask you, remember, n is always a positive integer. It could be 0, but bigger. It can be negative. Wouldn't you say that this is bigger? Whatever n squared is, any value you put in there, adding 1 to it is going to make it bigger than this. That's how you start. And then you put 1 over. Every time you put 1 over, this sign will switch. So basically, this is what we're saying. Think of this as a sub n and b sub n like the definition up there. Now, since we established this condition, make sure to put series on that. This is converge because p equal 2 bigger than 1. A p series, if you remember. And we've just shown that this is bigger than that. Therefore, the series n equal 1 to infinity, 1 over n squared plus 1 converge by the comparison test. Make sure you specify that at the end. So remember, not the sequence. You show the sequence is bigger, but 1 over n squared is not a p series. You have to put the summation on it, n equal 1 to infinity, for it to converge. Otherwise, that wouldn't work. And I'm going to do that on every problem, and I hope you're going to do that on every problem as well. I get to this problem. Same deal. If I start with 6, then we're safe. This is always positive. I take n minus 5 and n. I want to get rid of the number. So in this case, n is bigger. Any value of n that you choose, 6 or bigger, this is going to be bigger than that. So if I put 1 over, the sign will switch. 1 over 10 is bigger than 1 over 100. Now again, you put the series on that, and this is p series, p equal 1, therefore it diverge. By writing p, I know you mean p series. You don't have to say by the p series. So I've just shown that the smaller diverge. What does that mean? The bigger diverge as well. By what? By the comparison test. make sure to put that summation there, and make sure you write by what test. It's very important that you do that. I have another example, the same deal. I get rid of, again, I'm looking at 2n plus 1, consider it 2n plus 3. I want to get rid of 3. So looking at this, I know this is bigger than that. So again, 2n to n, if you add 3 to one side, it makes it bigger. 1 over will force that to switch. And again, make sure you put series. This is a geometric series, r equal 1/2, less than 1. Therefore, it converge. So by putting G, I know you mean geometric. By putting P, I know you mean P series. Therefore, the series n equal 1 to infinity of 3 over, oh, I'm sorry. If you multiply by 3, that doesn't change the value. You want to get this exact in there. So, 3 over 2 to the n plus 3 converge by the comparison test. This might seem like simple. Believe me, in calculus, this is a living hell. Here, they're telling us exactly what to do and what test to apply. And if I look at this problem, again, I could use the integral test on most of those. I would take n radical n plus 4. I'll get rid of the 4. Always the number. That's how we start. This is definitely bigger than that. 1 over will make this bigger. This is 1 over n. If I take n to the 1, n to the 1/2, you add the powers, that's 3/2. Again, you must put the series on it. This is p equal 3/2 bigger than 1. Therefore, this converge. Therefore, my series n equal 1 to infinity 1 over n radical n plus 4 converge by the comparison test. And we have one more test to go. Let me shift that up. Okay, that's not, there we go. And let me pick that example up so it matches. And here we have the last test we're going to study in this section. There are 10 tests altogether. We're only focusing on those in this class. So we have the famous ratio test. This is what it says. And this test is very useful if you are dealing with an exponential or a factorial. Given a series, here they say where a sub n is positive, that's fine. You take the limit as n approaches infinity of a sub n and a sub n plus 1. We'll talk about what that means in a minute. You take that limit and you get it to be a value. If this value that you got is less than 1, we say the series converge. Which series? This series. If the limit is greater than 1, we say this series diverge. And if it equals to 1, this test fails. You must use another test. So, test the series for convergence or divergence. And again, they're very specific. They say use the ratio test. If the test fails, use another test. So I'm glancing at this. I know this is geometric, it converges, but it says use the ratio test first. And let's see how this works. We take the limit as n approaches infinity of a sub n plus 1 over a sub n. That is the limit as n approaches infinity. A sub n is 1 over 3 to the n. It's right there. A sub n plus 1. Replace that n by n plus 1. That is the limit as n approaches infinity of 1 over 3n plus 1 divided by 1 over 3 to the n. That is the limit as n approaches infinity. Instead of dividing by a fraction, you multiply by the reciprocal. That is the limit as n approaches infinity, one of the properties of exponentials. A to the n multiplied by a to the n is a to the n plus n. If I could go in this direction, I can go in this direction. Like saying x squared times x to the fifth. Isn't that x to the 7? So, if I go backwards, I could say that must have been 3 to the n times 3 to the 1. Those cancel out. And that's the limit as n approaches infinity of 1/3. And we know the limit of a constant is the constant. Isn't that less than 1? Therefore, here I don't have to restate the actual series because it's the only one in there. Therefore, converge by RT for ratio test. So for exponentials, it always works. For factorial, it always works. Here, if I take the limit, oops, let me use a darker color. Let's go with this. Limit as n approaches infinity of a sub n plus 1 over a sub n. Right, a bit bigger. That is the limit as n approaches infinity. A sub n is literally what you see. A sub n plus 1. Replace each of those n's by n plus 1. So that is the limit as n approaches infinity of n plus 1 squared over n plus 1 factorial divided by n squared over n factorial. That is the limit as n approaches infinity of n plus 1 squared over n plus 1 factorial multiplied by the reciprocal of this. Now this limit, this is what I'm going to do. I'm going to swap those. I'm going to say this is n plus 1 squared over n squared. And I'm going to say this is n factorial over n plus 1 factorial. If you recall, n factorial is n times n minus 1 times n minus 2 times 3 times 2 times 1. Any factorial that you come across, that's the definition of factorial, and 0 factorial is 1. So, if I had 7 factorial, I could say that's 7 times 6 times 5, 4, 3, 2, all the way to 1. If I say 5 factorial, 5 times 4 times 3 times 2 times 1. Do you notice that's 5 factorial right there? So I could say if I have 7 factorial, that's 7 times 6 times 5, and I could put a factor. I could stop at any place I want and put a factorial there, because this 5 factorial is the equivalent of that. I'm going to use that analogy on this problem. First, I'm going to combine those into 1. And here, you look at which is bigger. This is bigger. So I leave the bigger alone, the smaller alone, and I start reducing that. That's n plus 1. What would be the next term? Subtract 1. You always subtract 1. If I subtract 1, isn't that n? And I'm kind of doing this business. I could stop anywhere I want and put a factorial. That's always going to be the case. Those cancel out. This is the limit as n approaches infinity. Can't I say this is 1 plus 1 over n squared times 1 over n plus 1? Isn't that a 0? That would be 1 squared and doesn't that approach 0, which is 0 less than 1? Therefore, converge by comparison test. Another factorial problem. So if I take the limit as n approaches infinity of 2 to the n plus 1 over n plus 1 plus 2 factorial. Instead of dividing, I'm going to multiply by the reciprocal automatically. Save myself some time and work. This is going to be the limit as n approaches infinity, and let's see how this works. I know that's 2 to the n times 2 to the 1. I know this is n plus 3 factorial, n plus 2 factorial divided by 2 to the n. That is the limit as n approaches infinity, so I know those cancel out. That's a 2. And isn't this bigger than this? So I start reducing that. I would say that is n plus 3 times n plus 1 less is 2 factorial. I could stop there because I could see that's what the top is. Those cancel out. I'm left with the limit as n approaches infinity of 2 over n plus 3. The limit as n approaches infinity, this will equal a 0 less than 1, therefore converge by the ratio test. Now, if the test didn't work, if I get a 1, then I use anything else, any other test that I know of. Next problem up, again, I take the limit as n approaches infinity, a sub n plus 1. And I'm going to divide that by what I see, a sub n. I'm going to combine those two. And here I'm going to write this as 4/3 to the n times 4/3 to the 1 over 4/3 to the n. So I notice here that those cancel out. And this is the limit as n approaches infinity. Here, that's 1 plus 1 over n squared times 4/3. So this will approach 0. That will be 1 squared times 4/3, which is 4/3. That's bigger than 1. Therefore, diverge by a ratio test. And the last example I have is the following. I'll try the ratio test on this. We would say, well, let's see. Let's take the limit as n approaches infinity of 1 over n plus 1. I'm going to change that slightly. 1 over n plus 1 minus 1, that's a sub n plus 1, divided by what I see. That is the limit as n approaches infinity of 1 over, isn't that just n? And instead of dividing, don't you multiply by the reciprocal? So I would say this is the limit as n approaches infinity of n over n, which is 1, minus 1 over n. That's a 0. I'll get the limit to be 1. That means it's inconclusive. That means the ratio test doesn't apply. So what can I do? Use another test. I could use the integral test. I could say take n minus 1 and n. Isn't this bigger? 1 over will make this switch. And I messed up. Let me start over. N minus 1 and n. This is bigger, right? If you let n equal 5, this is 4, this is 5. So this is bigger. 1 over will switch the sign. And again, make sure you write the series of 1 over n. That is p equal 1, diverge. Therefore, the series n equal 2 to infinity of 1 over n minus 1 diverge by the comparison test, because this is smaller. So this test, I couldn't use the ratio test, but I could use any other test. And that's pretty much it for this section.